Hello and welcome to the channel Understanding.Concepts.Of.Physics. Here we are today with the second video on oscillations. We had studied about periodic motion in the previous video, and today we are going to understand about what a linear simple harmonic motion is. So let's just quickly start with our topic, linear simple harmonic motion. Slowly and gradually you are going to build up the topics. Just keep watching one video at a time. Try to take notes, try to make notes, try to understand, try to recreate that notes, and gradually you will see that the chapter is going to get completed. So the first topic today topic which we are starting is linear simple harmonic motion. So what is a linear simple harmonic motion? The to and fro motion of a body along a straight line is called as a linear simple harmonic motion. So if there is a body which is just going back and forth along a straight line, then such a motion is called as a linear simple harmonic motion. Now the examples of this is motion of a swing, strings of a guitar, shock absorbers of a vehicle, atomic vibrations. All these examples we had discussed in the previous video, that is one video just before this, the first video of oscillation, and you can just go back to that video to understand more in details about these examples. Now today we are about to understand one equation, and for that I want you to focus on only one diagram at a time, and if you can see, there are three diagrams visible on the screen. What I want is you should not focus on the first diagram and you should not focus on the third diagram. Just focus on the center diagram, that is the relaxed state. Now the relaxed state is where the spring is just resting normally, nothing is happening, and this is where the block is, and the mass of the block is small m. So I have not written here, I'll just write it over here that mass is m. So mass will not change even if you keep this body in motion. So let's just quickly see what happens here. So nothing is happening over here. The resultant force is 0 because only force acting on this is gravity downwards and normal upwards. And here we are assuming that the friction is not there. So the surface is frictionless. This is one assumption we are going to make. So once the oscillation starts, once the body starts to oscillate, you will find out that this will be going on till infinite time, because there is no friction and there is no air resistance. So just try to fix it. We are not assuming friction. Only when we are considering damped oscillation at the last part of this chapter, we are going to consider friction. Right now we are not considering any friction. So there is only two forces, that is gravity downwards and normal upwards, and there is no other force. So I can say that the restoring force is 0. Restoring force means there is nothing happening, the body is at rest, the net force is 0. So body is in equilibrium. Now that's why it is called as a relaxed state. Now let's say if I pull this spring to the right. Now I want you to focus on the first diagram, the orange diagram. So if you see the spring has been elongated, and the mass has come somewhere around this position. Mass is not going to change, and I am holding this. Till the point I am holding this, gravity is acting downwards, normal is acting upwards, and my external force is to the right till the point I am holding it. And there is one more force, which is the restoring force, which is acting on the other side. That's why this block is not moving till I am holding it. But as soon as I release my external force, if I release my external force, you will find out that normal is balanced by gravity, Fg is gravity, normal is upward. So the block is not moving up and down, but because of this restoring force, the block is going to come behind. So the block is now going to come behind, and so that's why I have pointed here, restoring force is acting downwards. So note that when I gave the displacement to the right, the restoring force got developed to the left. Also you should note that the larger I pull on this side, right hand side, the larger the restoring force will be developed on the left hand side. That means force and displacement are directly related, and they always are in opposite direction as of now. Now what happens is this block comes at this center position, like we are again back to this position, but this block is not going to stop at this point because inertia says a body in motion will always be in motion. So this block is going to move behind. So here we come to the third, that is the green diagram. Now the spring is going to, if you see, spring has been coiled, it has been compressed. So when the spring is compressed, it has come to a point where it has come to a halt. Now if I hold it at this point, if I have just held this block at this point, then again gravity is acting downwards, normal is acting upwards, and now my external force, because I am holding it at this point, so my external force is this side, and the restoring force is trying to restore its position, and it is trying to push the block towards this, again the center position. Now till I am holding, this is the condition, the block is at rest. But as soon as I remove my external force, restoring force is going to dominate, and the spring is going to uncoil and again come back to the center position. And this will keep on happening till infinite time because there is no air resistance and friction. So this is what is happening in the compressed state and the relaxed state and the stretched state. Again, you should note that when the restoring force was to the right, as I showed you, gravity downward, normal upward, external force was this side, left side, and restoring force was on the right side. So when the restoring force was on the right hand side, the displacement was on the left hand side. So again, the restoring force is directly proportional to displacement, and it is oppositely directed. Why it is directly proportional? Because the more I press on this side, the more restoring force it is going to develop. The more displacement I give to this block, the faster it is going to come. The more acceleration this block is going to have, the more force it is going to have. There are some points I would like to highlight as, when it was at rest, this position was called as the mean position, or it is also called as an equilibrium position. And we say that the displacement is 0. And when it is to the positive side, the most extreme right hand side, we call it as x is equal to plus a. That is positive extreme position. So this is a positive extreme position, and I'll write as a. Now this a is also called as amplitude. And when the block was at the negative side, on this left hand side, we call it x is equal to minus a, and this is called as negative extreme position. So from now on, in the entire chapter, we are going to call the center position as mean position or an equilibrium position. A right position is called as positive extreme position, left position is negative extreme position. Now whatever I have represented that in the diagram, you can see I have written what it is, and you can just go through, you can pause the video and go through the things which I have just mentioned. Now what is happening in the stretched state or a relaxed state or a compressed state, whatever I have explained, those things I have written over here. So you can just go and have a look. When the displacement is to the right, the restoring force is to the left, and when the displacement is to the left, the restoring force is to the right. And in relaxed state, the net force is 0, that is the restoring force is 0, and we say that the system is in equilibrium. Now in all the conditions we have seen that the force is directly proportional to displacement, and it is always pointing to the opposite direction. So in order to remove this proportionality sign, I will multiply by a constant. So f would be equal to minus of kx. This k is basically a constant. Now this k is what is called as the Spring's constant or force constant, and the formula, the value for k would be equal to minus of f upon x. Generally this minus sign is ignored because minus sign is just showing you that the force and the displacement are always in the opposite direction. So then comes the unit. So force ka unit is Newton and displacement ka unit is meter. So Newton per meter is the unit for k, and in CGS system dyne is the unit for force and a centimeter is the unit for displacement. So you can just see how Newton per meter or dyne per centimeter becomes the unit for the spring constant or the force constant. And then the dimension is L1 M1 T minus 2. We can easily find out the dimensions for anything. So here we can define what our linear simple harmonic motion is. So linear simple harmonic motion can be defined by this method as well. However, we can define it as here as well, like Okay. um, a simple harmonic motion, linear simple harmonic motion is a periodic motion in which the force is directly proportional to the displacement, and it always points towards the mean position. So just go through this. In a linear simple harmonic motion is a periodic motion in which the force is directly proportional to displacement, and it always points towards the mean position. So that's the definition for linear simple harmonic motion. Maybe in the next video, because this video is becoming long, I would write that definition somewhere and give you a screenshot. So thank you so much for watching. In case you have not subscribed the channel, just subscribe the channel, share it to your friends and family, whoever can get the benefit out of this. Thank you so much. Have a nice day. Bye.